Today we're doing 8.2 angle bisectors of triangles. I don't have a fancy song for you this time, my apologies. There's some extra credit in it if you guys can write me a cool song and perform it for me, though. So angle bisectors, we know what angle bisectors are. We've discussed angle bisectors before. In fact, I'll just skip ahead to these theorems. We have an angle bisector theorem. So before we just had the definition of an angle bisector. And we defined an angle bisector as a ray that's between the two sides of an angle that divides that angle exactly in half, right? So our definition of an angle bisector that we used in proofs was we were told this was an angle bisector, and then we concluded that these two angles are congruent. And now we can go a little bit further, and we can say, well, if a point is on the angle bisector, then that means that point is equidistant from the two sides of the angle. So in this case, AC is congruent to BC. Those are congruent segments right there. And recall that when we get the distance from a point to a ray or a point to a line, we need to go perpendicular to it. So we can't go get this point like that. We have to be perfectly perpendicular. So that's why there's these 90-degree marks. To get the distance from A to C, we need to measure perpendicular. All right. This theorem also has a converse. The converse is just the same thing switched around, where we can say if we have a point that is equidistant from the two sides of the angle, so it's the same distance from this side as it is from this side, then we can say it is on the perpendicular bisector. So point C is equidistant from PA and PB, therefore it is on the angle bisector of PC. And we can conclude from that that this angle is congruent to that. Right? Similarly, how we can conclude that that distance is congruent to that. All right, so keep these in mind as we move forward. In fact, we're going to do a couple practice problems with them. So here we have, we just need to find LM. So we need to find this distance. The question is KM an angle bisector? Well, it's hard to see here, but there's two little congruence marks. So yes, KM is an angle bisector. Therefore, point M is equidistant from the two sides. So this is congruent to this, and ML is just 12.8. Right. Don't get too hung up on the computations there. For part B, it says the measure of angle ABD is what we need to find. The given is that the measure of angle ABC is 112 degrees. So here we have point D, and point D is equidistant from ray AB and ray BC, right? So therefore, ray BD bisects angle ABC because of the converse of the angle bisector theorem. Since it's on the angle bisector, that means this angle is congruent to this angle. And we could say that angle ABD is exactly half of angle ABC. So half of 112 is 56. All right, here's a few more. See if you can do a few more. So pause here. Hopefully you got 14.7 and 58 degrees for both of those. Okay, next up, a couple terminology words. Before we had a circle that was circumscribed around a triangle. Now we're going to inscribe a circle. So to be inscribed means we put it inside of a polygon. Usually we'll do triangles. In this case, when we inscribe our circle, the center of the circle must be what's called the incenter. So this is our second center of a triangle. We're going to have multiple centers of a triangle. In this case, the incenter is the center of a circle that just barely perfectly fits inside of that shape. So you can remember incenter because it's inside in. And in fact, we have an incenter theorem. So this incenter theorem is basically the same thing as the circumcenter theorem, but instead of doing perpendicular bisectors, we're going to do angle bisectors. So we're bisecting these angles instead. And when we bisect all three angles, we actually have done this in class as a construction. We're bisecting those angles, ba-doop, 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 ba-doop. We find that the point that they intersect at is the incenter. And remember, one of the properties of the points on an angle bisector is that they're equidistant from the sides. So that means PZ is congruent to PX, which is congruent to PY. And Z is just the point on this side, BC, that is perpendicular to BC. So it's therefore the closest point on that side to point B. Similar with here and here. Let's see if I can make a circle. See if it inscribes decently. Close? Yeah, pretty close. All right, so see, it barely touches all the sides. And that's our definition of a circle too, by the way, is infinite number of points around here that are equidistant from the center of the circle. So that's why it fits so well. All right, we're going to do this problem here. I know it's a little hard to see, but there's a triangle JKL, and then there's some values here. V, as it turns out, is the incenter. It says right here that JV and KV are angle bisectors, so therefore they're going to meet at that incenter. And that's how we can determine that V is the incenter. Then it asks us to find the distance from V to KL. So that's this distance here. It's a little hard to see, but since V is the incenter, we know that it's equidistant from all sides. So this distance is 7.3, so this distance also is 7.3, just like this distance would be as well. So all three of those red lines would be 7.3. All right, we also need to find the measure of angle VKL. So V to K to L is this angle up here. This one's a little bit more involved. We have to get clever here and figure out what angles we know and what we can figure out. So since V is on an angle bisector, or JV is an angle bisector, we can say that this angle is also 19 degrees, right? So that means that the measure of KJL, so K to J to L, is going to be twice 19, 38. Cool. We know that if this angle is 38 and this angle is 106, we should be able to calculate angle JKL, right? Well, 38 plus 106 is equal to 144. It combines these like terms. Subtract the 144 from both sides, we get angle JKL is 36. And then we're not quite there yet. JKL is 36, but we need angle VKL. So VKL is exactly half. And so 1/2 of 36 is 18. Cool. We did it. A lot of little wrangling there, but as long as we can remember the triangle sum theorem, that everything adds up to 180, and we can remember that these are angle bisectors, since it was given that they're angle bisectors, we should be able to deduce most of it. All right, I'm going to erase this part here, but go ahead and see if you can do 8 and 9 on your own. So pause here. Hopefully you got those answers. All right. Last little point is we need to compare our circumcenter with our incenter because it's really important to have these two down. So this picture describes 2 points. One is the circumcenter, one is the incenter. And as it turns out, we can always figure out which one the incenter is in this sort of situation because the incenter, in order to be where you're going to inscribe a circle, needs to be inside that triangle. The circumcenter, however, sometimes, at least in an obtuse triangle, the circumcenter can be outside of that triangle. So just keep that in mind, that the location sometimes varies. Right. Oops. Give away answers. So let's go ahead and fill this in. Please, please, please fill this in your book, because it's an important reference tool and you can use it to study. So the circumcenter, right? You can think of circumnavigate if you're going to walk around something or go around something. So you need to go all the way around that that triangle. That circumcenter is the point of concurrency of the segment bisector, or the perpendicular bisectors. Whereas the incenter is the point of concurrency of the angle bisectors. We just did that one. The circumcenter, again, think of your circle, right? The center of the circle is equidistant from the edge. So the circumcenter is equidistant from all of the vertices of that triangle. The incenter is equidistant from all of the sides of that triangle. And then finally, this one was covered already. The circumcenter can be anywhere inside, outside, or on the triangle. In the case of the incenter, it is always going to be inside. Okay, so some things to review there, but that's it. That's all I got. Have a good one.